Okay, any questions so far? Okay, so last time we reached to example maybe 3. Okay, so we derive the equation and then we solved it. Okay, and we obtained the amplitude as well. Okay, and we derived the and then we said that this is part, or this type of system is going to be moving in harmonic motion, and then you can find the period of oscillation, and you can find Fn equation. Okay, Fn is 1 over 2 pi square root of k over m, and also you can put Fn as 1 over 2 pi square root of g over delta if you use the equilibrium equation. And furthermore, you can put omega n as square root of k over m equal to square root of g over delta as well, which means that you can find the nature frequency if you know the statical deflection. Okay, or you can find the statical deflection if you know the other parameters k and m. Okay, so this was an example with m and k given spinning mass system, and Fn is 1 over 2 pi square root of k over m. The main thing here is that you use a consistent unit, convert k into Newton per meter. Okay, and then example 2 is cantilever beam of negligible mass carrying a mass at the free end is modeled as a spring and mass, where k is 3ei over L cube. Once you do that, you can find Fn, okay, which is 1 over 2 pi square root of 3ei over ml cube. And I gave a note about I, that is the moment of inertia of the cantilever beam in bending. Okay, and then we reach example 3. Okay, which is about water tank and column. And then we model it as a cantilever beam and mass, and then we model it as a spring and mass. So the nature frequency for part A will be omega n equal to square root of k over m. So, or if n equal to 1 over 2 pi square root of k over m, and k is 3ei over L cube. Okay, I is is pi over 64 d outer to power 4 minus d inner to power 4, and then we get 600.9. Okay, then we substitute in k and we find that k is 1545.6. Then before the end, one of your classmates said that f equal to pi over square root of pi, and this will give us the correct answer. And I didn't see that it is working. And we can apply this into the, for example, number 1. Okay, you will not get the answer. You can try. Okay, you will not get f equal to 3.941. Okay, so I don't know where is this coming from. I don't see any.
دكتور حصلت نفس الإجابة أنا الصراحة، بس إذا غلط خلاص غلط عادي.
اوكي، يعني تقدر تجربها. هذا انا قلت لك لا جربها على هذا السؤال example 1. انت
إيه
تقول
طلعت عندي نفس الجواب.
if n equal to pi over square root of delta.
إيه
we have all this, right? You can put pi square root of delta. How much is delta? 16.
إيه دكتور.
يلا طلع الجواب. Okay, the answer is 3.94. من عندك كالكوليتر عقيل؟
يطلع 0.78.
كم؟
0.78.
0.78. لا ما يصير.
24.83.
24 لا، بس احنا عندنا كم يطلع 3.9. عمار جاي بتقول نفس الشيء.
والله
ها؟
ما دكتور، آخر مرة طلعت عندي نفس الشيء بس.
اوكي لا لما ما يطلع نفس الشيء. زين يعني هذا اعطيتك مثال الحين عملي. اوكي you can يعني see what is the units of this, huh? If maybe something else, maybe it's not hertz, something else. Okay, and then as a continuation, I just put this in lecture 3. Okay, so this is the continuation of the example number 3 with I and K we reached to from the previous lecture is 1545. Okay, so omega n is square root of K over M because this is the model of spring mass system. Okay, so this will give us omega n equal to square root of K over M. K is calculated as 1545. Okay, and divided by M. The mass is not given. We have the weight is given equal to 6 times 10 to the power 5 pound. Okay, and we know that equal to mg, and from here we can find m equal to w over g. Okay, the value of k is given as pound per inch square. Pound per inch. So g has to be per inch per second square. So it is 6 times 10 to the power 5 divided by g, which is 32.2. This is feet per second square, multiplied by 12. Okay, so 32 is feet per second, feet per second square. We multiply by 12 inches divided by 1 feet. So the answer will be in inch per second squared. Okay, which becomes equal to 386. Okay, so this becomes 6 times 10 to the power 5 divided by 386.4. And in the equation for omega n, we divide by m. M is W over G, or you can multiply by G here, K multiplied by G. So it is 1545.6672 times 386.4 divided by 6 times 10 to the power 5. We get omega n equal to 0.9977 radian per second, which is almost 1 radian per second. The natural time period, this is also part of part in A, is to find the natural frequency and the period of oscillation, okay, which is 2 pi over omega n. Tau n equal to 2 pi over omega n, 2 pi over 0.9977 equal to 6.2977 seconds. The second part is to find the response. Okay, so part B is to find the response if the initial condition is given. So let me just read the question for part B. Determine the vibration response of the water tank. The vibration response means X for all time. Okay, that is the vibration response. It is different than the amplitude. Amplitude is the peak value. But when it says response, it means X. Due to an initial transverse displacement. Now this direction is called the transverse. Okay, يعني horizontal, means horizontal. And of 10 inches. So this will be as X at 0 equal to 10 inches. and no initial velocity is given. So we will assume that x dot at 0 is 0. So we have only initial displacement. Okay, so initial displacement equal to 10. If you go back to what we did in the previous lecture about the response, we derived the equation for the response. Okay. Okay, this is not the amplitude, this is the solution, and the solution means response of vibration. That is x of t. Solution means response, which means x of t. Okay, it is given finally, after we use the initial conditions, we get x equal to x dot 0 divided by omega n sine omega n t plus x at 0 cosine omega n t. Okay, here it is amplitude of vibration is obtained with A0. Okay, that is the amplitude of vibration. Here, this is the amplitude. We find finally A0. Okay, but amplitude, it means the peak value. Okay, so with initial conditions given, we can use the equation. If you don't want to use this equation, you can use x equal to x dot at 0 divided by omega n sine omega n t plus x at 0 cosine omega n t. Since x dot at 0 is 0 given, and this is 10 inches, then the answer will be 10 inches cosine 0.9977 t. Okay, this is the obtained omega n, 0.9977 t. Or he's using this form, it is also the same, that x of t equal to A0 sine omega n t plus phi 0, and you apply initial conditions, you will find that A0 is 10 and phi 0 is equal to pi over 2, which will reduce to x of t equal to 10 sine 0.9977 t plus pi over 2, and sine plus pi over 2 is cosine. Okay, so it is 10 cosine 0.9977 t, and this is the response. This is the response of the water tank for all time. Then part C is to find the maximum values of the velocity and acceleration experienced by the water tank. The maximum velocity and maximum acceleration, since this is harmonic, or you can differentiate, this equation to get the velocity. This is the response, which is x. You can differentiate to get the velocity equation, and it is 10 times omega n, which is 0.9977 cosine 0.9977 t differentiation of cosine is minus sine, or he's differentiating sine here. Okay, and this becomes the coefficient of the cosine is the peak value. So you don't have to do this. You can directly find the maximum velocity from this equation, which is A0 omega n. We know this is harmonic, and it will be A0 times omega n. Okay, so it is 10 times 0.9977. As you can see, it is same as this, the coefficient of cosine, and this becomes 9.977 inch per second. And acceleration is differentiating the velocity. We get minus 10 times 0.9977 squared sine. So the coefficient of you don't need to include the negative. This will be the maximum acceleration. Or as we know from chapter 1 that this is harmonic motion and the maximum acceleration is a omega n square, and here a0 omega n square. So it is 10 times 0.9977 square equal to 9.954 inch per second squared. Okay, so this is part of, this example, which is C, is similar to what we did in chapter 1 about finding the peak values of velocity acceleration. Okay, so as when you find the amplitude, just use this equation to find the maximum velocity and use this equation to find the maximum acceleration. But you have to find A0, that is the peak value. Example 4, if you have no question, we can proceed. Okay, determine the natural frequency of the system shown below in figure A, this figure. Assume the pulleys to be frictionless and of negligible mass. Okay, so this assumption is important because this will reduce the system to single degree of freedom system. Okay, so if as you can see, there are two springs and pulley arrangement. If the pulleys are with mass, then this becomes maybe 3 degrees of freedom. And if the pulleys are not frictionless, then the tension in the cord will be different on the sides of the pulley. So with those two assumptions, that the pulleys are frictionless and of negligible mass, the system becomes a single degree of freedom system. Let me just draw this from, this is like given as isometric. Let me just take the view from side view. So it will be, this is a cord and this is a pulley, and it will go around the pulley. Okay, here is supported by a spring of stiffness K1. Okay, the rope will go to the second pulley, which is supported by another spring of stiffness K2, and then go around the pulley to carry the mass M. Okay, the pulleys are named 1 and 2. Okay, and they are assumed to be massless and frictionless. One more thing we can add in assumptions is that the cord is inextensible. Okay, we have cord is so it will not change in length. That is delta L is 0, not elastic. The springs are massless. Okay, we have only this mass. Since we have pulley arrangement, the type of motion is called dependent. Okay, we have dependent motion, as we did in dynamics. من شرح لكم الداينامكس؟
دكتور زهير.
Okay. Okay, so you did the pulley arrangement, right? Part of chapter maybe 1 is about kinematics, and then one section is about dependent motion. Here we have I can give, first of all, we need to do kinematics. Okay, because what you want at the end, this is an actual system. what you need is to find the model. The model should be a spring mass system. Okay, that is the system, because with the dependent motion, we can assume this is single degree of freedom. This is M, and this is the K effective or equivalent. Now, if the mass is moving with X, okay, I want an equivalent system to this system that moves with also X for the mass M with K equivalent. So this is omega n here is, I know, is square root of K over M, right? But here I don't know what is the omega n. I have to find the model. With the assumptions we did, that the masses of the pulleys are massless and frictionless, and that the spring masses are neglected. Also, the cord is inextensible. Then we can use the kinematics. The kinematics, I'm going to give the location or the position of pulley 1 from, this is the data from where I measure the position of the pulleys and the mass. So I'm going to call this x1. And the position of pulley 2 from the same datum is x2. And the position of the mass, okay, you can just take this from here, is x. So from the length of the cord, we can find L equal to length of the cord okay, so equal to what? Equal to x1 plus this part of the cable portion, which is x1 minus x2, plus this portion of the cable, which is x minus x2. So plus x minus x2. Now, if you open the brackets, you will get 2x1 minus 2x2 plus x. Plus a constant, usually we just neglect. What is the constant? The constant is, since we are measuring the length of the cord, this is also part of the length of the cord, and this is also part of the length of the cord. So this is like C1 and C2, and then it is just a constant. This is the length at, let's say, position 1. If you take another position, okay, then you will get L2. So this is L1, and then L2 for another position. And that x1 move to x1 prime, the new position. So this it means it will go down, and then the new position will be here, and I can call it just x1 prime. And the same thing for x2 prime and x prime. So the new position will be 2 x1 prime minus 2 x2 prime plus x prime, and of course C is the same. There will be no changes in C. Now delta L equal to L2 minus L1 equal to 0, right? Because this is inextensible cable, as we assume. Cord or cable. Then when you do the subtraction, you will get 2x1 prime minus x1. I'm just going to, okay, I'll keep it as it is. 2x1 prime minus x1 minus 2x2 prime I did L2 minus L1, so this will be minus 2x2 prime minus x2 plus x prime minus x, and c minus c will be 0, equal to 0, because delta L or L2 minus L1 is 0. Now x1 prime minus x is the change in position. Okay, it is not the position, it is the change in position, because you will take this part. This is the change in position. The same thing for x2. Okay, similarly for x2 prime minus x2 and x prime minus x. So at the end, you will get the equation of 2x1. I'm going to call this x1, small with this small with lower cases, x2 and x. Okay, so it is 2x1 minus 2x2 plus x equal to 0. Therefore, x equal to 2 minus, this will be minus x1 plus x2. So I have a relationship now between x1 and x2. Now physically, the positive direction we assumed is downward. Okay, so let's take let's see the relationship between x1 and x2 and the direction of those two. If x1 is taken, if x is downward, then the pulley number 2. Okay, we name this as number 2 and this is number 1. Okay, if x is positive, it means that x2 is also positive, will go downward with the mass, and x1 will go, or pulley 1 will go upward. So we have pulley 1 and pulley 2 are always in opposite direction. We can use that, so we can change the sign. This is always addition. Okay, we know that pulley 1 and 2 are, they move in opposite direction all the time. For all time. So that x, when x2 is positive, x1 is negative, and negative becomes positive. And when x2 is negative, x1 is positive. So it is always addition. So if we take the absolute value, okay, if you take the absolute value, you will have x equal to 2 x1 plus x2. Okay, this is the absolute value. It is always addition. That x is always twice x1 plus x2. So you take into consideration the sign of x1, then it will be addition. So it is always addition. This is the relationship between, the final relationship between x, x1, and x2. So further thing we have to do is we draw the free body diagram of each pulley. Okay, we draw the free body diagram around pulley number 1 and around pulley number 2 and around the mass. Okay, around the mass, for the assumption that the cord is inextensible, the pulleys are frictionless and massless, the tension in the cord is the same at any point. Okay, so when you take the mass then the tension in the cord will equal to W. Okay, so this is the mass. You will have the mass is the weight is acting downward, and there is tension upward here. And for equilibrium, this is for equilibrium, that T equal to W, the tension equal to the weight. And the tension at any point on the cable is the same. So when you take the pulley number 2, you will have tension on both sides of the pulley downward, and equal to W and equal to W. And the spring force by Hooke's law is K2 times X2. X2 is the change in length, the change in position. So of the pulley, which is also the change in length in the spring, X2. So the spring force by Hooke's law is K2 X2. And you can use for equilibrium, sum of forces equal to 0. You will get that K2 X2 equal to 2W, or X2 equal to 2W over K2. Okay, so for equilibrium, we have T equal to W here, and we have K2 X2 equal to W, or X2 equal to W over K2. Okay, for pulley number 1, we have the cord is going around the pulley, so it is tension T and T here, and T equal to W, T equal to W. And the spring force by Hooke's law is K1 times X1. So sum of forces equal to 0. So this is equal to, and then you rearrange, you get K1 X1 equal to 2W. Okay, or X1 equal to 2W over K1. So we have for equilibrium again, all of them for equilibrium, that sum of forces here is also equal to 0. So we have two expressions for each x. I mean, we have expression for each x. X1 equal to 2W over K1, and X2 equal to 2W over K2. We can substitute in the kinematics relationship here. So we put we obtain that X1 equal to 2W over K1, and we find that X2 equal to 2W over K2. So therefore X becomes 2, and then this is 2W over K1 plus 2W over K2. And we can simplify this by taking 2W outside as common factor. This becomes 4W times 1 over K1 plus 1 over K2. Okay, and then this becomes K1 when you add the fractions, K1 plus K2, all divided by K1 plus K1 times K2. Okay, so this is X equal to this. And put the value on one side. And to arrange the equation as Hooke's law, this will be K1, K2 divided by 4 K1 plus K2 W X. K1, K2 divided by 4 K1 plus K2 times X, which is Hooke's law. So therefore, the K equivalent is equal to 4 equal to K1, K2 divided by 4 K1 plus K2. Which means that the model we assumed as a spring mass system will have K equal to K1, K2 divided by 4, K1 plus K2. Okay, so we reach to the model. This is the actual system with pulley system, and this is the model. And for the model, we know that omega n equal to square root of K over M. Okay, so he's deriving the same thing. He find K equivalent and then substitute in omega n equal to square root of K equivalent over M. Equal to K1, K2 over square root of K1, K2 over 4M, K1 plus K2 in radian per second. So this is the final equation for the expression of the natural frequency. So although this is a pulley arrangement system, but we can model this to a spring and mass with some assumptions and reach to the simpler model, which is a spring mass system. The pulley system, okay, is modeled as a spring and mass, but K is given as an expression. So in case you want to study the effect of K1 on the natural frequency, it is simply changing K equivalent. By changing K1, you are changing K equivalent, or you changing K2, you are changing K equivalent, which is the value of K. Okay, so this is the procedure. Okay, I will print, there is, the next section is about rotation or torsional vibration of shaft, but before that, let me just show you the questions in tutorial number 2. Okay, here is just a few seconds. Okay, in the tutorial 2, you will find there is a table here at the end. Okay, is about spring stiffness. We have here 2 springs, we call them in series, and those we call them parallel. Now, in series, it means that you have a system. Let's say it is with the stiffness K1 and then another spring with the stiffness K2, and then it is the mass. Since the masses are negligible of the springs, this can be made equivalent to one spring and the same mass. So this is K equivalent. For series, we call this one series arrangement. We know that the force in each spring is the same, but displacement is different. So that you can have K equivalent is 1 over K equivalent equal to 1 over K1 plus 1 over K2. Or K equivalent equal to, when you add those two, you get K1 plus K2 divided by K1, K2, or you get K equivalent equal to K1, K2 divided by K1 plus K2. It's called series. And if you have parallel, it means that the springs are undergoing the same deflection. So this is K1 and K2. Here in series arrangement, force is the same. For equilibrium, if you just consider the equilibrium, that force is the same on each spring. And here, displacement is the same on each spring. So each spring will undergo X1 or X, just call this one as X. There's no X1, X2. Okay, of course, when you do this, it means that the mass is guided. Usually we don't add this, but we mean that there is no rotation. Okay, so here we have guides that will not allow the tilting or rotation of the mass. Okay, in this case, we have K equivalent is simply equal to the addition K1 plus K2. Okay, and the model will be the equivalent system will be one spring with mass. Okay, moving with X, where K equivalent equal to K1 plus K2. And then, of course, you can get omega n is square root of K equivalent over M. And the same thing you can do here. Omega n is square root of K equivalent over M. If you have two springs in series, if you have three springs in series or more, you can do the same thing. It will be just for the series, it's going to be addition. One of the K equivalent is equal to the sum of the reciprocal of all the stiffnesses. If the springs are in parallel, K equivalent is equal to the sum of all the stiffnesses. This way is taking this system into a model, so that with the model we know what is the natural frequency. But if you keep it this way, and you work on the equation of motion, it will be, you will maybe derive at the end, you will derive the same thing, but instead of doing all the analysis we did, we can just simply add the springs, since those are massless. And in this chapter, or up to chapter 4, there is we are only solving or investigating single degree of freedom system. So even if there is mass, we will see in some of the sections of this chapter how to deal with spring with mass. Okay, so in the tutorial we have here questions. I will jump to question number 7, so that we have a direct example about the arrangement of springs. Okay, question number 7. A 50 kilogram block is supported by the spring arrangement shown. The block is moved vertically downward from its equilibrium position and release. Knowing that the amplitude of the resulting motion is 60 millimeter, determine the period and frequency of motion, the maximum velocity and maximum acceleration of the block. Now, those springs are in series or in parallel? We have 3 springs. Now, if you just pay attention, if you paid attention to what I said, that for parallel, the force is the same. For series, I mean, for series, the force is the same. on each spring. And for parallel, we have displacement is the same. So we can apply this on this problem. Now, the 3 springs are fixed at one point. This is fixed here. And also this is fixed here. So all the springs have at one point and they are fixed. The other point, they are attached with the mass. So the deflection, if you take deflection downward x, it means that this spring will go downward x, so it will have deflection x. And also the 2 springs below the mass also will undergo distance equal to x. So the 3 springs are in parallel. Okay, so this is the answer. They are in parallel because they have the same deflection, the absolute value, and doesn't matter if it is under tension or compression. They undergo the same distance. So they are in parallel. They are acting as on the mass with the same. You can just apply Hooke's law. It is k times x. To prove that they are in parallel, if you assume that x is downward positive, then you draw the free body diagram of the mass. If you take x positive downward, then the spring at the top of the mass will be under tension or compression.
Tension.
Okay, so it is tension. It's a tension. What is the effect, the direction of the force on the mass? We draw the free body diagram of the mass. So if the spring is under tension, it means it is pulling upward with k times, let's just call it k1, k1, k2, k3. So it is k1 times x. The springs here below the mass will be under tension or compression?
Compression.
So compression, good. So the compression, it means they are pushing the mass upward with k2x and k2x. When you apply Newton's second law, sum of forces equal to mx double dot, we have the downward is positive. So it is minus k1x minus k2x minus k3x equal to mx double dot. So it is minus k1 plus k2 plus k3 times x equal to mx double dot. So they are in parallel. As you can see, they add up as we do in parallel. So you can either go this way, following Newton's second law, or you use the idea that the springs are in parallel and then K equivalent is K1 plus K2 plus K3. When you arrange this equation, you get mx double dot plus K1 plus K2 plus K3 times x equal to 0, which is mx double dot plus K equivalent times x equal to 0. So directly you can use omega n equal to square root of K equivalent divided by m, which is the addition. The units are given in kilonewton per meter. You have to convert to Newton per meter. It is a 24 plus 12 plus 12, which is 24 is 48. Okay, so this is square root of 48 times 10 to the power 3 divided by 50 kilogram. That will give us the mass. Once you that will give us the nature frequency. Then you can find maximum velocity is equal to omega n times x. How much is x? We called it before a. Knowing that the amplitude of the resulting motion is 60 millimeters, so it is given. So x60 is a, and you can use here times x and x equal to a. Okay, I mean by capital X as the amplitude. Okay, and you substitute here 60 millimeter multiply by omega n, and x double dot maximum, which is the maximum acceleration, is omega n squared a. Okay, that's it. Okay, we'll see you inshallah next time to see more problems in this tutorial, and maybe we move to lecture 4 as well. Okay, see you next time.
مع السلامة دكتور، يعطيك العافية.
Thank you.
Thanks.